want to take a look at the energy aspects of working with a system of objects. Now, the energy that we're looking at is truly just mechanical energy. Now, keep in mind, mechanical energy basically consists of an object's kinetic energy plus all the forms of potential energy. I say all the forms because by this point we've only dealt with gravitational potential energy. However, there is also elastic potential energy that we get to when we talk about oscillations, or some people already talk about that when they deal with a mass attached to a spring. And so we're looking at these energy aspects when an object is associated with a system. I don't know why I did that. So anyway, the kinetic energy is an interesting 1/2 mv squared. The kinetic energy is associated with the object in and of itself. If the object is part of the system, great, it has kinetic energy. If it's not, great, it could have kinetic energy. As long as the object has velocity, it has kinetic energy regardless of the system that it might be part of. And so the kinetic energy of an object really isn't associated with the system, but we can't ignore it either. The things that really play are potential energy. Even if you haven't talked about elastic potential, it's important to keep in mind that potential energy and potential energy, the real simple definition is stored energy. Well, the question becomes, where is this energy stored? And it depends upon the type of potential energy. Gravitational potential energy, the energy is stored in a gravitational field. I'm just going to write gravity because I'm lazy. Elastic potential energy, it's stored up in a spring block combo. So this is obviously a system. And again, if you haven't gotten to elastic potential, you will, and you can see that when we're dealing with those problems, it's a potential energy problem. I want to spend time talking about gravitational potential energy because that comes up a lot with the system. And it's not unusual where they define a problem and they define the system where it might include the Earth, it might not, and you have to evaluate the energy considerations. And so that's what I want to take a few minutes today to take a look at. Okay, let's look at gravitational potential energy. And if we look at the expression that's on the formula sheet, it's written as delta UG is equal to mg delta y, which I like a lot. A lot of people, instead of delta y, put h there. Perfectly understand why they do, but I like the delta y because it conveys the fact that gravitational potential energy is the change between two positions, and that is, to me, it's important to recognize because that emphasizes the fact that this is energy stored up in a system, and the system is the mass and Earth system. So this is energy stored in the gravitational field of the mass Earth system. I know the Earth is part of this system because we have that term right there, the acceleration due to gravity, and this comes from the Earth. This also gives us a reference point, which is the change in y, which our initial position is typically the surface of the Earth. But you know, the main thing is this gravitational acceleration. Where does it come from? It comes from the Earth. So the Earth has to be part of the system with gravitational potential energy. So let's say let's just look at a situation, and we have the Earth, and we have a ball that's a 1 kilogram mass, whatever, and it's 2 meters above the Earth. If the ball is just sitting there, and if we're holding it up there, it's not moving. The ball has no kinetic energy. When we let it go, the ball starts falling. Obviously, it's picking up speed, it's being pulled down. Since the velocity is increasing, its kinetic energy is increasing, and right at that point, right before it hits the Earth, we have 40 joules of kinetic. Did I do that right? 20 joules of kinetic. Because this is equal to the gravitational potential, 20 joules of kinetic energy. Now, so let's look at this. We have gravitational potential is 20 joules here, and gravitational potential is 0 joules. So, I apologize, it's a little bit off the screen. So, let's look at our system. If the system is the ball, so system, ball, kinetic energy is not conserved because the kinetic energy goes from 0 to 20 joules magically. It's not conserved. If the system is the ball, it has no gravitational potential. Because in order to have gravitational potential, we need to include the Earth in our system, and we're not. We're only including the ball. And so when we look at the system of the ball, the only energy it has is kinetic energy. Nothing else. If the system is the Earth, it's got no kinetic, it's got none. I like none better than 0. It has 0 joules of kinetic, no gravitational potential, because we need at least 2 objects for our system. Maybe undefined would be better terms for the gravitational potential there. If the system is our ball Earth, now we have conservation of energy. Now this kinetic energy, which goes from 0 to 20 joules, is good or cool because our gravitational potential goes from 20 to 0 joules. And there's a nice balance there. And we have this balance because we now include all bodies in our system. And once we include all the bodies in our system, now we can start looking at conservation of energy. This is how the system aspect with energy is a little bit different than with the forces that I talked about with Unit 6A. Let's talk about our gravitational potential energy expression a little bit more. And we're limited by it. We're limited to where our acceleration due to g is a constant, which is only true near, here's where I meant to do my air quotes, near the Earth's surface. Near surface. If we're not near the Earth's surface, we cannot use that expression for gravitational potential because our value for g might not apply. And so the question becomes, there's really 2 questions. The first question is, what the heck do we do? And the second question is, when are we not near the Earth's surface? Well, I'm not going to answer the second question because all the situations that we run into will either be near the Earth's surface or obviously not. Like we're comparing the sun and the moon. A satellite orbiting the Earth is not near the Earth's surface. So we're not talking something fine line, and I'm not going to say 2 miles above the Earth is not near. I'm not going to do that because we're either going to be obviously near the Earth or not. And when we're near the Earth, boom, that's it. When we're not near the Earth, we have to do something else. Now the equation, which is just simply horrible, minus G M1 M2 over R. And this is just simply a horrible looking expression. It's derived from the gravitational force, universal gravitational force expression. Here's the masses of our two bodies. The distance between the two bodies, our universal gravitational constant. This is the gravitational potential energy stored between M1 and M2. Now, the so-called elephant in the room with this equation is that negative sign. We have negative gravitational potential, and that's a real hard thing to explain and to understand. I can tell you this. That negative sign comes from our derivation of this expression, which we're not going to get into. And it comes from the fact that when we derived this expression, we assumed that gravitational potential was 0 at infinity. Making this assumption caused us to have that negative sign. Now, if you're calculating the total energy of a satellite, you have to include the negative sign. And you very well might get a negative total energy. The weird thing is, it doesn't matter, because this is the potential energy at one particular position. What's really important is if we move one of the objects and we experience a change in potential. And so this negative sign there, while it might seem odd, quite simply put, it's not important. What's important is the change in gravitational is important. If the change in gravitational potential energy is greater than is positive, we did some work. If it's negative, the object did some work, or the gravitational field did some work. And so it's this change that's important. I think I'm going to do one quick example with this gravitational potential energy, just to kind of illustrate how it would work. I was going to do an example with total energy, and obviously there it is, but I'm not a big fan of the example, and quite honestly, of all the things to worry about, this isn't one of them. So let me erase it. There. Don't worry about all that type of stuff. If that's the only thing you don't understand in AP Physics 1, you're fine. So that's what I have for Unit 6B, the energy aspects with objects, with systems. Unit 6C, which is our momentum, is a pretty significant part of this chapter. Until then, good luck.